Okay, we're starting our next unit, which is going to be on distribution. So the first thing we need to talk about is just positions in the distributions and how we arrange that information. So if you take the SAT, they end up sending you a piece of paper with this on it, and it says, it talks about a writing 10 of score of 510 is 50% of other people scored lower. And so you can see this, which is the percentile rank in each one of the SAT. So if you scored a 610 on the math, you were in the 77th percentile. Well, what does that mean? How do we interpret that? Well, what that means is that if you took everybody who took the SAT and you arranged their scores from lowest to highest, right, then what you would find is that you scored better than 77% of people who took the test. Incidentally, if you did that same thing, you'd see a 600 as a 75th percentile, which means that this is the third quartile, because the third quartile is the 75th percentile. The median is going to be the 50th percentile, because you'll be better than half the kids. The first quartile will be the 25th percentile. So let's see here. So I know that, and so here we can see all the percentiles. Incidentally, they also will report the mean and the standard deviations on all three of those exams. So math has the highest mean score, but also has the highest variability. So when we do a percentile, all you do is you say what percentage of the observations are less than it. So Jenny earned an 86 on her test. How did she perform relative to the rest of the class? So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. The class has 25 people in it. Now, 3 people, she beat 21 people. Right? You don't count yourself. You only count the people that scored lower, and so she got a 21 out of 25, or around 84% of the, so she would be the 84th percentile. Now, since you only count people that you beat, but you count yourself as part of the population, what you'll go here is that you will see at the top of this, there is never a 100th percentile. There can't be. Because even if you're the top scorer in 100 people, then you beat 99 people, but there were 100 people in the class, and so you're the 99th percentile. So you can be the 99.999 percentile, but you can never be the 100th percentile in a ranking. So then they can do something else, which is known as an ogive. And they take those relative percentiles and they show them as a graph. And that's what's known as a relative frequency graph or an ogive. I know it seems like it should be ogive, but they say ogive, I know. And so here's an example of an ogive of, below is the cumulative frequency plot that shows the height in inches of college basketball players. So what this is saying is it's saying that, hey, right here, 74 inches is the 50th percentile. So half of all college players are taller than 74 inches, which incidentally is 6'2" for people who can't convert that. So half of all college basketball players are 6'2" or taller. So the question then asks, okay, well, based on this ogive, what is the IQR? So, well, here's what we're going to do. We know that quartile 1 is the 25th percentile, and we know that quartile 3 is the 75th, 75th percentile. So there's Q1. And there's Q3. So Q1 is 71 inches. Q3 is 77 inches. So the IQR is 6 inches. So the 6 inches centered around the median contains 50% of all college basketball players. So 50% of all college basketball players are between 71 and 77 inches. Right? We can get percentiles, we can get IQR, we can get medians and everything off the ogive because they correspond to percentiles. All right, sorry, I'm going to tell a little bit of a story here. If you go to Boston, there is a bridge that's Harvard Street, I think, that goes across the basin of the Charles River. And the Harvard Bridge goes to a major university, MIT. And don't ask me why. Harvard Bridge goes to MIT. Harvard's further downriver, or further upriver. But the bridge is long, and I don't know if you've been to Boston in the winter. It's not terribly lovely. And during winter, the wind's really blowing hard. And so there's an MIT fraternity brother who was crossing the bridge, and he had his hat pulled down, and the wind was blowing in the middle of winter as he was crossing the bridge. And the bridge goes on forever. It's a very long bridge across, wide open, water on either side, just you're getting pummeled by the weather. And so he decided that he wanted markers on the bridge to show how far across it was. And so he got the pledge of his fraternity together and said, hey, listen, you need to go out on the bridge and make markings on the bridge across so I know how far I am across the bridge and how much I have left. So just go out there and paint. And they're like, okay. Now, MIT, if you didn't know, is one of the top technical engineering and science schools in the country, if not the top. And so they immediately ask questions like, okay, well, what units of measure do you want? Do you want meters? Do you want yards? Do you want feet? And the guy said, you know what? That's too much work. For all of you, who's the shortest guy? And the shortest guy was a guy by the name of Oliver Smoot. And he's like, I want you to measure Smoots across the bridge. And so what they did is they actually went out and they put poor Oliver Smoot at one end of the bridge, and they had him lay down, and they made a mark at the top of his head, and they made a mark. And they had him get down and put his feet and his head down and made a mark. And they measured the distance across the bridge in smoots. And so this is a picture from the bridge. By that point, you're 100 Oliver Smoots across the bridge. Now, this seems like a really silly unit of measurement. Smoot was 5'7", and it is. It's a completely whimsical thing of measurement. But the thing is that as long as you were on that bridge, you knew where you were because that was the measurements they used on that bridge. And so the silly measurement then became useful because it was a long bridge, there'd be a car accident, and the cops would, in their police report, say it was near the 110 Smoot mark because it was marked on the bridge. They'd call a tow truck and they'd be like, hey, we're at the 50 Smoot mark westbound. And people knew where to go for the tow truck. To the point that when they resurfaced the bridge, instead of doing the standard 6-foot expansion joints on the concrete, when they redid the bridge, they made the expansion bridges 5'7" or 1 Smoot. Now, what does this whimsical story have to do with statistics? Well, once again, the idea that there's a unit of measurement that's useful for that bridge and comparing yourself to the bridge is going to lead us to an idea that you learned in Algebra 1 and hit again in Algebra 2, which is z-scores. And z-scores is what allows you to compare apples to oranges. And here's the example. Rory McIlroy won the 2011 U.S. Open Golf Tournament at the Congressional Country Club over in Maryland with a score of 18 under par. Second place, Jason Day, was 6 under par. This was the lowest score in U.S. Open history. Now, the U.S. Open is played at a different location every single year, and they spend like several years getting the course ready and making it as difficult as possible to play. So generally, people aren't very far under par at the U.S. Open because they've made the course so difficult. And Tiger Woods in 2000 shot a 12 under par to win the Open and played that year at Pebble Beach. And at the time, that was considered one of the most dominant displays of golf at the time. So the question, in second place, Ernie Els was 3 over par. For people who don't know golf, is a negative score is better. So the more negative your score is, the better. Tiger Woods was the only player with a negative score. And generally in a tournament like the U.S. Open, I think there's like over 100 people entered, and Tiger Woods of those 100 was the only person to break par. So the question was, who was the most dominant? And you can't compare this negative 18 to this 12 under because they play them on different courses. Pebble Beach is this beautiful course on the west coast of California that's up against the ocean. Congressional is a beautiful country club up in western Maryland, but they are different courses. They completely play differently, and it's difficult to compare them, especially when they're groomed so specifically for the U.S. Open. So what we're going to do is we're going to use that z-score. And the z-score in and of itself is meaningless. Z-score is you take Rory's score, negative 18, and you subtract the mean score for the entire tournament. This is, of all the players in the tournament, this is their average score. And you'll notice we're using mu and not x bar because we're comparing to the entire population. And then we're going to divide by the standard deviation of the entire population. And if we do that, we get a value of negative 3.39. Now, what does that negative 3.39? It's a unique measurement only for Congressional and for the 2011 U.S. Open. And it's saying in 2011, Rory McIlroy was 3.3 standard deviations below average. And the standard deviation is defined by the players in the tournament. Tiger Woods was 12 under, but the average score in that tournament was a 12.07. And the standard deviation was actually smaller. And so when we do Tiger Woods, what we see is gets a z-score of negative 4.11. And so what we're seeing here is that Rory McIlroy the interpretation was 3.39 standard deviations below average, which in golf is good because a lower score is better. Tiger Woods was 4.11 standard deviations below average. So comparing these, and remember, standard deviation is defined by the group that played this weekend, which are the top 100 golfers in the world at that time. So at the U.S. Open, Rory McIlroy was 3.39 standard deviations better than the average person in the field. Tiger Woods was 4.11 standard deviations below the average player in the field. So z-score is like the Oliver Smoot type measurement. It's a measurement that only works when in its own context, and the units on the z-scores are standard deviations. So a z-score of 2 means you are 2 standard deviations above average. A z-score of negative 1.5 means you are 1.5 standard deviations below average. And the standard deviation is defined by the population. And so to go back to my apples versus oranges, let's say we were to say, is this a good apple? Well, we could say the z-score of the apple was 1.1. And the z-score of the orange was 1.8. Now, this doesn't tell us whether an apple tastes better than an orange. It tells me that this apple was 1 standard deviation bigger, let's say we were going on weight, than a normal apple, where the orange was 1.8 standard deviations bigger than average. And so what we're saying is that this orange is better than most, is better than most, to a larger degree better. Sorry, let me start that all over. The orange is to a larger degree better than the average orange, then the apple is better than the average apple. Don't worry, we're going to do lots more of this in class tomorrow. I'll see you then.